in section 6.1 and in chapter 6 in general, we're going to look at power series solutions to differential equations. And we're going to start by reviewing some of the information from power series that you should have seen perhaps in calculus too. So we recall that a power series in the variable x minus a, or in x minus a, is an infinite series of the form the summation from n equals 0 to infinity. We have x minus a to different powers with these constant coefficients c sub n. If we write out the first few terms, when the first index term is 0, this gives us c0 times x minus a to the 0 power, so that term would disappear. It would be 1, so we just get c0. When n is 1, then we get c1 times x minus a to the first. When n is 2, we get c2 x minus a to the second power, etc. Okay, so this is what we mean by a power series. And it's kind of important to note, and we'll have to pay attention as we move throughout this chapter, is what is the index of summation, where does it start at? It does not necessarily need to start at 0. In particular, if some of your first terms here were 0, then you could really start this at, like, let's say n equals to 2 or 3 or whatever. But the way that's presented in the definition is that n equals to 0, but just be aware that that doesn't need to be the start of your summation. We say that such a series is also said to be centered at a, so whatever the x minus a value is, whatever sits behind a negative sign here, that's going to be the center of the power series. Okay, it's kind of the expression that would make this x factors equal to 0. So if we looked at something like this, the summation from n equals to 0 to infinity of x plus 1 to the n, then this one would happen to be centered at negative 1. Some students will just kind of remember just the opposite of what's in the parenthesis with the x. So if you see x minus a, then it's centered at a. If it's like x plus 1, then it's centered at negative 1, etc. Okay. For instance, if we look at this particular power series, the sum from n equals to 0 to infinity of 2 to the n times x to the n, this one would be centered at 0 because there's no x minus anything. You could think of it as x minus 0 raised to the nth power, which means that this power series is centered at 0. And those coefficients, the c sub n's, those would be given by the expression 2 to the nth power. We want to recall a couple important facts about power series. Convergence. So what do we mean by convergence? Well, a power series is convergent at a specified value of x if its sequence of partial sums converges. That is, if the limit as capital N approaches infinity of this sequence of partial sums, which is nothing more than the limit as n approaches infinity of the sum starting from n equals to 0 up to capital N of Cn x minus a to the n if it exists. Okay. If this limit does not exist, then we say that the series is going to be divergent. Okay. In general, these power series will converge for some values of x and diverge for other values of x. Okay. And we say that every power series has what's called an interval of convergence. This interval of convergence is the set of all real numbers x for which the series converges. The center of the interval of convergence is the center A of the series. So this interval of convergence, it's centered at the center, which is A, and it's going to have, in general, some what we call radius of convergence. The radius of the interval of convergence of a power series is called its radius of convergence. If r is greater than 0, then a power series converges for x minus a less than r. In other words, if it's centered at A, we can go within r units either to the left or to the right, which means that the absolute value of x minus a needs to be less than r, and it will certainly diverge for all x minus a that are greater than that radius of convergence. It may be the case that the series may only converge at its center, in which case it would only converge for the x value x equals to a. Then we would say that it has a radius of convergence which is equal to 0. Okay. If the series converges for all values of x, then we would say that the radius of convergence is positive infinity because it will converge for all real numbers. We can recall that we can rewrite this absolute value inequality. This is the same thing as saying that x is between a minus r and a plus r. We always will need to check to see specifically whether or not we get convergence at these endpoints of this interval. So a power series may or may not converge at the endpoints. Furthermore, what it does at one endpoint has no influence on what it does at the other endpoint. So it might converge for both endpoints, it might converge for the left but not for the right, or vice versa, or perhaps it may not converge at either endpoint. But we'll kind of have to test each endpoint on an individual basis. Okay? We also have the concept of what's called absolute convergence. In the interior of its interval of convergence, a power series converges absolutely. And when we mean by absolute convergence, it means that the sum with absolute value bars converges. Okay? You might recall from calculus 2, but in general, absolute convergence is a pretty strong condition. Absolute convergence implies convergence, but not the other way around. Okay, to give you an example of this. Okay. So, if a series converges absolutely, in other words, if it converges with absolute value bars, then it will converge without the absolute value bars. Okay, but the converse is not true. Just because a series converges does not mean that it will absolutely converge. Okay? To give you an example of this, consider the alternating sum, the summation from n equals to 0 to infinity of negative 1 to the n over n. Okay? This series here converges via the alternating series test. Yet, if you were to try to look at the absolute value of this thing, this would be equal to the sum from n equals to 0 to infinity of 1 over n, which would be a divergent series. This sum would diverge. So be very careful. Absolute convergence implies convergence, but not the other way around. So the series will converge absolutely within its radius of convergence, centered at A. The radius r means you can go r to the left and r to the right, and it's going to converge within that band. It will diverge outside of that interval, and the endpoints are kind of to be determined. You would need to check, based upon your concrete series that you're given, what happens at each of the two endpoints. Okay. This brings us to the ratio test. Again, hopefully you've seen this before previously, but convergence of a power series can often be determined by the ratio test. Suppose that C sub n is not equal to 0 for all n, and we have our power series. Then suppose that the limit, as n approaches infinity, of our general term evaluated at the n plus first index divided by C sub n x minus a to the n, this is equal to the limit as x minus a. You can pull that outside the absolute that limit because it doesn't depend upon n. It's the limit as n approaches infinity of c to the n plus 1 divided by c to the n, which is equal to L. This series will converge absolutely if L is less than 1, and it will diverge if L is greater than 1. And when L actually equals to 1, then the test is inconclusive, which kind of demonstrates why it's always inconclusive at the endpoints. Let's take a look at a concrete example of this. It says, find the interval and the radius of convergence for the following power series. We have x minus 3 to the n divided by 2 to the n divided by n. So this is kind of the series that we have. Let's go ahead and see, first of all, what is the interval and what is the radius of convergence for this series. If it helps, if you want to kind of see it written more explicitly, using this kind of sum notation, this is the sum from n equals 1 to infinity. You can think of it as kind of like 1 over 2 to the n times x minus 3 to the n. So the center is going to be equal to 3, And the thing that would be like our c to the n would be this coefficient here. It's being played by the 1 over 2 to the n times n. To do this, let's go ahead and do the ratio test. We want to investigate the limit as n approaches infinity. We want our general term with the n plus 1 substituted in for the n. This is going to give us x minus 3 to the n plus 1 divided by 2 to the n plus 1 times n plus 1 all over x minus 3 to the n divided by 2 to the n times n. This is equal to the limit as n approaches infinity. Good old school keep, change, flip. Like this. This is equal to, let's simplify this, the limit as n approaches infinity. First of all, the 2 to the n, we can cancel with 2 n powers of 2 down here, but we're still going to have a 2 in the denominator. We can cancel n powers of x minus 3 with n powers in the numerator, but we will still have an x minus 3 up top. And so we have the following. This is the absolute value of x minus 3 over 2 times n over n plus 1. This part we can factor out because it has nothing to do with the limit n. So this is the absolute value of x minus 3 over 2 times the limit as n approaches infinity of n divided by n plus 1. And then this whole limit is equal to 1. We know that this thing will converge, absolutely, when the absolute value of x minus 3, first of all, we can take the absolute value of the fraction. That's going to be the absolute value of the numerator over the absolute value of the denominator. This needs to be less than 1, which implies that the absolute value of x minus 3 needs to be less than 2. That will provide us with the following interval. So it's going to be x minus 3 has to be less than 2, but greater than the negative 2. If we add 3 to every part of this inequality, we get 1 is less than x is less than 5. So a couple different things. So first of all, the interval, we're not quite sure yet, but we know that the radius, looking over here, we know that it's centered at 3. So that's our center, and our radius of convergence is going to be equal to 2. It still remains to check what happens at each of these two endpoints. So let's check at the left endpoint what happens when x equals to 1. If we take and plug 1 into our series, this is what we're going to get. We get 1 minus 3 to the n divided by 2 to the n times n. This is equal to the sum from n equals to 1 to infinity of negative 2 to the n over 2 to the n times n. I can break the term in the numerator apart. Think of it as negative 1 times 2. This is the same thing as negative 1 to the n times 2 to the n over 2 to the n times n. Now that we've done that, these cancel, and we're left with the summation from n equals 1 to infinity of negative 1 to the n over n, which is a very popular, this converges via the alternating series test. So it does converge for the left endpoint. So I can say the interval of convergence is at least 1 less than or equal to x less than 5. Now let's go ahead and check convergence at the right endpoint. So what happens when x equals to 5? Well, if we plug 5 into the sum, we get the sum from n equals 1 to infinity of 5 minus 3 to the n divided by 2 to the n times n, which is the sum from n equals 1 to infinity of 2 to the n divided by 2 to the n times n. Those cancel, and so this becomes the sum from n equals 1 to infinity of 1 over n, which is a divergent p-series. So this diverges. So the interval of convergence, if we want to write it like this, it's going to be from 1 to 5. The left endpoint is included because it does converge for x equals to 1, but the right endpoint would not be included because this series diverges for x equals to 5. And again, typically if the question is about interval and radius of convergence, we want to apply that ratio test as we did in example 1.